Salutations, fellow chemists. Today we're going to be looking at energy profile diagrams, but before we get started, it's important to know some key definitions. So the first one is activation energy, and this is the minimum energy, and this energy is required by, this is the important bit, required by reactant particles. That will be important very soon. Reactant particles in order for a reaction to take place, and that will become clear. That says happen, by the way. That will become clear when I draw the diagram shortly. Next, we need to know about exothermic reactions. You can tell me some examples here. Combustion is an example here. Neutralization is a good example as well. And an exothermic reaction is a reaction that gives out energy to the surroundings. So I'm going to just write gives out energy to surroundings. And this is going to give you an overall negative energy change. So negative overall change. That will also be clear when we draw the diagrams. And next we need to look at endothermic reactions. These are opposite to exo, so we should expect these to take in energy from the surroundings this time. And a good example of these here would be photosynthesis. It requires energy from the sun to allow this to happen. Another one as well, any decomposition, thermal decomposition, for example. Decomposition, and that's when you need to heat something up to break it down to something else, and that's thermal decomposition, but there are other types of decomposition as well. So here, this is going to give you a positive overall change in energy. And now we're going to look at the graphs to see how this translates in terms of the energy differences between your reactants and your products. So just like magic, we have an energy profile diagram set up here. We're going to look at what it is for an exothermic reaction. So you can see here, we have energy on our y-axis. So we're looking at how the energy changes, and on the x-axis, when we go forward in time or as the reaction progresses. Or you can also look at this as the reaction coordinates. So you might have different names over here, but all of this just means as we go forward in time and as the reaction happens. So we know that at the beginning in time, we have reactants. So I can label this here, reactants. And for an exothermic reaction, remember we mentioned that this here gives out energy to the surroundings, and that gives you an overall negative energy change. So we are going down in energy when we get to the products. When we get to products here, the products are more stable than the reactants, so the reactants' energy will be higher than our products here. That means energy can be given out to the surroundings. I'm going to swap pen, and we're going to go for the red one here. But what we must show is a nice curve going up and then down like so. And I'm going to show you clear labels as well, just to give you an idea of what we have here. So first thing is, remember we said the activation energy, is the minimum energy required by reactants to give us our reaction. So we have to start an arrow from the reactants to the top of our curve here. And I'm going to label this as EA. And we're going to make it clear what that is in a second on that side. And what you also need to be aware of is from reactants to products, the difference in that energy is what we call the overall energy. In this case, we're going to go from reactants down to products here. I'm going to label that as delta H. In this case, you can see we're going down. So I'll put delta H over here. And for an exothermic reaction, as I said, that is negative because we go down in energy. Reactant level is higher than the product level. So let's label this here. That's our activation energy. Activation energy. And the delta H here is negative for exothermic, and that's the overall energy change. So overall, in terms of energy, our reactant's energy is higher than the products. And that is the key information that you need to know for this here. But also the activation energy, which we're going to move on to in another video, is the energy required to break all of the bonds in the reactant as well. So I'm going to move on to that in another video, so stay tuned. For now, we're going to move on to endothermic reactions. So I'll see you in the next frame. Excellent. So now we're focusing on endothermic reactions and the energy profile diagrams. And we should remember, in this case for endothermic reaction, because they take in energy from the surroundings, we have to put energy in, and therefore the energy level of reactants is below that of the products. So product energy is higher. It's the opposite to our exothermic one. And same as before, you have to draw a nice curve starting from your reactants and ending at your products like so. And the labels are exactly the same. We start from the reactants to the top of our curve there, and that is the activation energy. A lot of students, however, put two heads on the arrow, so they put another label over here. Do not do that. Make sure your arrow is only showing one head here, otherwise you will not get the mark. So what I mean by that is double-headed arrows are not allowed. Okay, next thing here is exactly the same as we saw before, which is the overall energy change must start from your reactants. It's the difference between reactants to product. But the difference in this case is that we have to go up to the reactants. So the overall energy here should be positive. So very quickly, I'm going to summarize. So bear with me whilst I wipe the board. Fast forward here. So we're back, and just a quick summary of the two of these. So remember, for our endothermic one here, our products level is going to be higher than our reactant level. So that means our overall energy change, the delta H, is going to equal a positive number. That's important to remember. And for our exothermic, here you see that the reactant level this time is higher than the product level. So our delta H, our overall energy change, is going to be negative here. And a quick reminder that your activation energy always starts from your reactant level and goes to the top of your curve. Do not use double-headed arrows. And a good analogy for this here is going up and down the stairs. I remember going up the stairs takes a lot of energy, so you can think about that there as the endothermic one, where you start low with your reactants, always reactants at the start of a reaction, and then you go up the stairs to the product. So that means you have to put energy in, and that there helps me to remember what this looks like. If I remember what the endothermic one looks like, then it's easy to apply to the exothermic one. So hopefully that is nice and easy for you to remember how to approach our energy profile diagrams. Make sure you like, make sure you subscribe, and I'll see you in the next video.